everyone. So today we're going to be talking about systems of equations. We're going to start off with some vocabulary. We first need to know what the heck a system of equations is. So it's going to be a set of two or more equations that are to be solved simultaneously. These are linear equations. And then we need to know what a solution is of this system of equations. And that's going to be, and this is important, it's an ordered pair that makes both equations have to be true. Super important there. Okay, so we're going to start off by seeing our three ways to solve systems. And those three ways that we're going to solve systems today are going to be by graphing, substitution, and elimination. Not going to lie, graphing ain't my favorite. We're going to start off by solving systems by graphing. First thing we're going to do is graph these. I actually don't like this setup here. We're going to see a little bit later on why there would be a better way to solve. But when we graph, we've been so used to seeing linear equations lately that we like to keep things in good old slope-intercept form. Y equals mx plus b. So that's what I'm going to do. So I'm going to take my first equation, the top, whoops, that's a y. That's also an equal sign. I'm going to take 2x plus y equals to 1. And I'm going to get that into slope-intercept form. So to do that, I have to subtract 2x from both sides. And we're going to get y is equal to negative 2x plus 1. Then I'm going to take that bottom equation and I'm going to do the same thing. This is going to look a little weird because we're going to have the y on our right side. So I'm going to subtract both sides by 8. I'm going to have x minus 8 equals to 2y. And I'm going to divide each term by 2. So we have y equals negative 1/2 x minus 4. Okay, now I'm going to go ahead and color code these for a reason. So I probably don't have the best colors here, but we'll try red and green. So I'm going to graph this first line, y equals 2x plus 1. Remember, the two things we need to know are the m and the b. So I'm going to begin here at 1. Because my rise, which needs to be a fraction, is negative 2 over 1, I'm going to go down 2 and to the right 1, down 2 and to the right 1, and down 2 and to the right 1. And so we have, I'm actually going to go up 2 also because I can. So we have this line here. So I'm going to go ahead, graph my line. And now I'm going to graph my second line. Again, the only two things we need to know are our slope and our y-intercept. So I'm going to go ahead and graph that. Again, don't worry that this equation is backwards. Totally fine. So I'm going to start here at negative 4. Since my slope is 1 over 2, I'm going to rise 1 and run 2. Rise 1 and run 2. Rise 1 and run 2, if I could. Okay, so we should see that we have this line here. What we notice is those two lines intersect. Again, going back to our solutions of our system of equations, we were told that by definition it's an ordered pair. So this is why it's so important for us to recognize points on the coordinate plane. What is the location of this point? And this is going to be at 2, negative 3. So 1, 2, and then 1, 2, 3. And I know my graph's not super great, so that's why everything's going to be a little bit off. But if I went ahead and substituted my x and my y, I would know that 2 times negative 3 in the bottom equation would be negative 6, and negative 6 plus 8 is 2. So that one's going to check out. And in my top equation, 2 times 2 is 4. 4 plus negative 3 is going to be 1. And again, going back to that definition, both equations must be true. And we just saw that they were in that first one. Okay, so let's look at number 2. I actually like this example a little bit better because we have an x and a y. Again, this is solving systems in two variables, but when we graph this, what do we have to remember about this? X equals 2 are what kind of lines? That's right, vertical. And y equals, and no other variable, is going to be a horizontal line. So this is going to be actually one of my favorite things to graph. I wish we could always have everything in x and y. So x equals 2, we know this is going to be here at 2, 1, 2. And I'm just going to draw my vertical line as straight as I possibly can. And then I'm going to draw my horizontal line at y equals -3. Ooh, that was not super great. But what we notice is those two lines, again, will intersect. And they intersect right here at this point, 2, 3. Again, that's going to make both of these equations true, so we're good to go. Love vertical and horizontal lines. I love example 3. This is my favorite example. Why? Because everything's already in slope-intercept form. I don't have to do any work. This is why I like graphing these types of equations the best. So what's going to happen here is something weird, first of all. So I'm going to graph. We remember our slope and our y-intercept. Again, we want that slope to be over 1 so that we can rise and run. So I'm going to graph my first line. I'm going to start at 4. And then I'm going to rise 3 and run 1. And because I can, I'm going to go down 3 and to the left 1. And we're going to make this line. Next, I'm going to graph my second line. Again, we want to have our slope as a fraction. So we have a slope and our y-intercept. So I'm going to go ahead and graph that. I'm going to start at -3. I'm going to go up 3, over 1, up 3, over 1, up 3, and over 1. And I should notice that I have this line. Sorry, that wasn't very over 1. Ooh, that was a terrible line. Sorry, guys. This is what happens when you don't use a ruler. And what do we kind of notice about these lines, aside from this green one's a little shaky? Is there what? They don't intersect, so they must be, that's right, parallel. And so this is what happens when we have parallel lines. So we've seen 2 examples where we have an intersection and 1 where they're parallel. What does that mean? We're going to find out later. And then we have our last one, number 4. Okay, not gonna lie, kind of hate this problem. But because we can, I'm going to graph both of these by intercepts. We remember how to graph. And again, we want to make the graphing as easy as possible. So again, if I look at my first one, I have an x-intercept. That means we're going to cover up our y. So what times 2 is going to be 6? Well, we know that's going to be 3. So our x-intercept is 3, 0. And our y-intercept, if we look at this, cover up our x, what times 3 is going to be 6? Well, we know that's going to be 2. So we have our x and y-intercepts there. We're going to do the same thing with our bottom equation. I'm going to find my x-intercept first. I don't know what's going on there. And we are going to cover up our y. So what times -8 gives me a -24? And we see that that's going to be a +3. And I'm going to cover up my x and find out what times -12 will give me a -24, and that's going to be a +2. Something should look very interesting right here, but if it doesn't, that's okay. So I'm going to go ahead and graph my green line first by intercepts. So 3, 0 and 0, 2. Here's this line. Okay. Next, I'm going to graph my second line with the intercepts at 3, 0 and 0, 2. And I'm going to graph that line. What does that mean? First of all, we should notice something interesting is happening. I have one line on top of another line. We're going to find out what that means later. Now we're going to solve systems by substitution. So we learned how to graph. We know that already. We can see that it's where those lines will intersect or not intersect or are the same line. But now, how do we solve by substitution? And I actually love this. If we look, what we notice is x plus y is equal to 6. Then I notice in my second equation that x is by itself. And so what I know is that x is actually equal to y plus 2. So what I'm going to do is I'm going to substitute. Anytime I see an x in my other equation, I'm going to substitute in that y plus 2. What does that mean? Well, let's see. So since I said x was y plus 2, this actually becomes y plus 2 plus y equals to 6. All I did was substitute the y plus 2 where the x was before. Now I'm going to just solve this equation like I'm used to solving equations. So I'm going to combine my like terms. Y plus y is 2y plus 2 equals to 6. Get my constants on one side, my variables on the other. And so I get y equals 2. But here's the great thing. We're not done yet. What? Remember, going back to our definition, we said it was an ordered pair. And an ordered pair, what do we have to have? That's right, an x and a y. And what do I have right now? Oh, I just have a y. So now, this is kind of the nice part. I get my y right here. So I already know one piece. So what I'm going to do is decide which equation would be easiest to substitute to get x. Either one is going to be fine, but because I already have x by itself, I'm going to take that y and now I'm going to resubstitute that back in. So x is equal to 2 plus 2. And what's 2 plus 2? 4. So now we know that x is equal to 4. But again, since we said that we had to have an ordered pair, we have to write this as an ordered pair. Ordered pairs, remember, are always x, y. So we're going to have 4, 2 as our ordered pair. And this is going to be our solution. Kind of confusing, I know. We're going to try a couple more examples. So let's look at number 2. So on number 2, we have x minus 2y equals to 8 and 2x plus y equal to 8. Now on this one, I don't have some variable completely by itself. So I need to isolate one of those. Either one is going to be fine. I can either add the 2y here and have x by itself, or I can subtract the 2y here and have y by itself. Not going to make a difference. We can do whatever we want. But since I like to keep everything positive, I'm going to go ahead and manipulate this top equation. So what I am going to do is add 2y to both sides, and that's going to give me a new top equation. It's going to give me x equals 2y plus 8. So what I notice here is I have my x by itself, and what is x equal to? Well, it's equal to 2y plus 8. So anytime I see an x, hey, I see one right here, I'm instead going to put in 2y plus 8. But before we do that, going to get one step harder. What does it mean when a number is next to a letter? Multiply. So this is really going to be 2 times, make it really obvious, multiplication with our parentheses, 2y plus 8 plus y equals to 8. Now I'm just going to solve like I'm used to solving. I'm going to distribute combine my like terms, plus 16, subtract, and isolate my variable. So y equals negative 8/5. Okay, so I have my y. I'm going to substitute this y back into either, well, I actually have 3 choices now. Original top, manipulated top, original bottom. Not going to matter, but since my x is by itself here and I'm looking for my x, I'm going to go ahead and substitute my y back into the manipulated top equation. So x equals 2 times negative 8/5 plus 8. Not a super great problem here. Want to make this a fraction. So put my 2 over 1. So I'm going to have x equals 2 times negative 8 is negative 16/5 plus 8. Again, we have to work with our fractions here. We can't forget all that fraction work that we did. Want to have my common denominators. My common denominator between these two is 5. So we have negative 16/5 plus 40/5. When I go ahead and add negative 16 plus 40, I do get positive 24/5. So now that I have my x and my y, I can write my ordered pair. And remember, all ordered pairs need to be written with x first and then our y. And so there we go. let's look at our next example. I know this one was bleh because of the fractions. Okay, so on number 3, we have y minus 2x equals 0 and 3x plus 7y equals 17. Okay, so if we look, again, I want to have one variable by itself. Hopefully we're deciding which equation looks easier to manipulate, and hopefully we see that it's going to be the top. Now I can get either variable by itself, but which variable is going to be easier to isolate, the y or the x? Hopefully we're seeing that it's going to be the y. So I'm going to go ahead and manipulate that. So to do that, I'm going to add 2x to both sides. And we know that 0 plus 2x is just going to be 2x. So our new equation is just going to be 2x. Y equals 2x. If we want to go ahead and put the plus 0, we can. Totally fine. And again, I now have my y by itself. So what is y equal to? Well, we said it was equal to 2x. So now anytime I see a y, I'm just going to substitute that 2x in there. So I'm going to go ahead and rewrite my bottom equation. So again, remember, a number next to a variable means multiply. So 7 times 2x equal to 17. I'm going to go ahead and multiply my 7 times 2x, and we get 14x plus 17. When I combine my like terms, I get 17x equals, whoa, sorry, I meant equals to 17. Then I'm going to divide both sides by 17, and x is going to be 1. But wait, we're not done yet. Now that I found my x, I can go ahead and substitute. Again, I can substitute back into my original top, my original bottom, or my manipulated top. Which one is the easiest? I'm going to go ahead and say manipulated top, so I'm going to substitute my x. So y equals 2 times 1. And what is 2 times 1? 2. So now that we have that, again, by definition, we have to have an ordered pair. So what's going to be my ordered pair? 1, 2. All right, guys, now it's time for you to try. So I'm going to give you guys one example to try on your own. Hopefully you guys didn't see the answer. Pause the video, try it, and then let's see if you get the correct answer. The big reveal! Hopefully you guys got -4, 3. If not, look back closely at your work. Remember, this is our time when we find the biggest addition, subtraction, multiplication, just basic algebra mistakes, dropping signs. So be very careful with that. This time, we're going to solve systems by elimination, and this is probably maybe the most confusing part of how to solve systems, or the most confusing way. So the first thing we're going to do is we have to understand that we're going to eliminate something. So we're going to look at our two equations, and we're going to decide if we want to get rid of our x's or get rid of our y's. Notice that they're both written in standard form. This works very well when our equations are written in standard form, but we're going to see some special cases a little later on. So if we look, first thing, hopefully when we look at this, we decide that we can eliminate our y's. Why do we want to eliminate our y's? Well, if we look closely, we see that one is a positive 3y and one is a negative 3y. So the first part of elimination is going to seem very easy. All I'm going to do is just add these two equations together. 2x plus 4x, that gives us 6x. What's 3y plus a negative 3y, or 3y minus 3y? Hey, we can eliminate that. Shouldn't have done that so dark. Equals 13 plus 17 is 30. So now how do I get this x by itself? Well, I'm going to divide both sides by 6. So x is going to equal to 5. But again, that crazy definition is coming back to us. It has to be an ordered pair. It has to have an x and a y. Now that we found x, we're going to have to substitute it back into either one of the equations. Not going to matter which, so I'm going to go ahead. I'm just going to use my top equation. So I'm going to substitute this 5 back in to where my x is. Boop. So I'm going to get 2 times 5 plus 3y equals 13. This is why I should not have made that huge of an x. So 2 times 5 is 10 plus 3y is equal to 13. whoa, I don't know what I'm doing there. I'm going to go ahead and subtract 10 from both sides. Now I can do that. So 3y is going to equal 3. I'm going to divide both sides by 3, and I'm going to end up with y equals to 1. Okay? But again, that crazy definition, it's rearing its ugly head. We have to have an ordered pair. So what's going to be my ordered pair once I find my two variables? It's going to be 5, 1. So let's try another example of elimination. So this one, first thing we're going to look at, we have both of our equations. Which variable looks easier to eliminate? If we look at this, hopefully we're going to focus in on those y's. Again, y, because we have a positive y and a negative y. Over here, they're both positive. We'd have to do some manipulation. We'll see that in a bit. So I want to get rid of my y, so I'm just going to add these two equations together. I'm going to be very careful not to cross anything out. So 3x, our y's are gone, and 5 plus 4 is 9. Going to go ahead and do some algebra, and we get x equals to 3. Once we do that, we can go ahead and decide which equation looks easier to solve. Again, it's not going to matter. I'm going to go ahead and use this top equation only because there's no coefficient there. I want to make this as easy as possible. So 3 plus y equals to 5. When we subtract our 3 from both sides, we're going to get y equals 2. But again, this has to be an ordered pair. So our order pair is going to be 3, 2. And that is going to be our answer. Now I'm going to have you guys try one on your own. So take a moment and check that, and we'll come right back with the answer. Ready for the big reveal? Hopefully we got the ordered pair 1, -2. So the next way we're going to see to eliminate is actually not going to be as easy. What we said with elimination is we like to try and eliminate one of our variables, either the x's or the y's. We've been lucky in the first two examples because we had a positive and negative y. But do we see that here? No, not so much. So what I'm going to do is I need to decide which variable I want to manipulate. I'm going to, again, look at my y's. Don't worry, it's not always y's. It just happens to be that in these examples. So to do that, what I'm going to do is I know I have a positive 3y on both of them. One of them needs to be a negative. So I'm going to have to multiply everything by a -1. It's not going to matter which equation we manipulate here, but I'm going to go ahead and manipulate my bottom equation because that just looks easiest to me. So when I go ahead and I multiply both sides by -1, I end up with -1x minus 3y equal to -7. I'm going to go ahead and rewrite my top equation even though nothing happened to that. I just want to keep everything nice and aligned. So now that I have that, what I can do is still go ahead and just add like we've been doing for elimination. So now we're going to see some eliminating. 2x minus 1x is going to be 1x or x. The 3y's will now cancel out, equals to 8 minus 7 is going to be 1. So we found our x. Again, we have to have an ordered pair, so I'm going to substitute this back in. Which is the easiest equation to work with? I'm thinking maybe the bottom one, but again, it's not going to matter. So I'm going to go ahead and I'm going to substitute that 1 plus 3y equals to 7. So all I did was substitute my 1 in for the x. And then I'm just going to solve this equation. That's why it's so important when we learn how to solve equations that we really understood that. Because we're seeing it all the time. So now that we have our y equals 2, again, remember, solving systems, we have to have an ordered pair. So our ordered pair here is going to be 1, 2, and that is going to be our solution. The next example that we're going to see with solving systems by elimination is going to be one of the harder ones. If we look at this, what we notice is I have to, again, decide if I want to eliminate my x's or my y's. On this one, we're going to have to do a little bit more of a manipulation than we did on the last example. So if we look, I'm actually going to go ahead and choose to eliminate my y's. The reason is because I have a positive and a negative. But remember, to eliminate, they both need to be the same number. So what's common between 6 and 2? Hopefully we realize that the least common multiple between 6 and 2 is going to be 6. So what I'm going to do, since I already have one positive and one negative, is I'm just going to go ahead and distribute a 3 to every single term here. So my new bottom equation is going to be 15x minus 6y equal to 42. Since nothing happened to my top equation, I'm just going to go ahead and rewrite that over again. 3x plus 6y equals to negative 6. Now I'm going to go ahead and solve this just like I would with elimination. Just going to add both of these two equations together. So I'm going to go ahead. 3x plus 15x is going to be 18x. I already learned my lesson not to eliminate my y's, but I'm going to get rid of those because 6y minus 6y is 0. And negative 6 plus 42 is going to be a positive 36. Do a little bit of algebra here that we're used to as far as solving equations, and we get that x is equal to 2. Now that we have our x, we can go ahead and substitute it back in. I can substitute it back into my manipulated bottom equation, my original bottom equation, or my top equation. Just because I feel like I haven't worked enough with my top equation, I'm going to go ahead and just substitute it back in there. But again, it will not matter where we substitute this back into. So that 2 is going to go substituted in for our x. So 3 times 2 plus 6y equals to negative 6. Going to go ahead and just do a little bit of algebra here. And we end up with y equals to negative 2. But again, we're not done yet. These have to have an ordered pair. So our ordered pair here is going to be 2, negative 2, and we're done. Our last example as we're solving systems by elimination is going to be by far the most difficult. So again, because it's elimination, I need to decide which variables I want to eliminate. Because I have a positive and a negative with my y's, I'm going to choose to eliminate both of those. But if I look closely at my coefficients, I have a 3 and a 4. So I can't just manipulate one of these equations. So what I have to do right now is actually manipulate both. So I'm going to think really hard about what 3 and 4 have in common. What's the least common multiple between those two? Hopefully we got 12. So what I'm going to go ahead and do, to make this a 12, I have to multiply everything in my top equation by 4. To make this a 12, I need to multiply everything in my bottom equation by 3. So I'm going to go ahead and write my manipulated equations here. So remember to multiply everything or distribute that 4. So everything needs to be multiplied by 4. So we have 8x minus 12y equal to negative 4. And here on our bottom equation, we have 9x plus 12y equals to 72. So what I'm going to go ahead and do right now is add like I have been doing with my systems, and 8x plus 9x is going to be 17x. My 12y's are going to cancel out, and negative 4 plus 72 is going to give us a 68. I'm going to go ahead and divide both sides by 17, and we get that x is equal to 4. Once I get my x, I can decide what I want to substitute back into. I can substitute back into my bottom manipulated, bottom original, top original. None of these look super great. I'm just going to go ahead and substitute this into my bottom equation. The reason is because I have all positive numbers here, and I kind of just want to work with that. Even though that 24 is a little large, I'm just going to deal with it. So 3 times 4 plus 4y equals to 24. So 12 plus 4y is equal to 24. Just do a little bit of algebra here, and we end up with y being equal to 3. But again, we're not done yet. How do I make this an ordered pair? Well, it's going to be 4, 3. And now we're done. Now it's time for you guys to try one on your own. So if we look closely, why don't you guys go ahead and try this one on your own. Pause the video, then you guys are going to see your answer. Hopefully you got -2, -1. If not, look back closely at your mistakes. Again, this is where we make a ton of algebra mistakes. The last type of systems that we're working on today are actually special systems. So the first thing, if we look here on number 1, what we notice is there's actually no order to this. It's not quite in standard form. It didn't look like there's y equals, so we can't really graph. And even the substitution, there's like no variable completely by itself. But if we notice on this, all we have to do is get the x by itself. So to do that, I'm going to subtract 6y and add 8 to both sides. I don't know why I just did that backwards. So if we go ahead and do that, what we end up with is x equals to -6y plus 8. I know I did a bunch of crazy math there. Since I didn't do anything here to my x, what we should remember is once we have a variable that we can get by itself, we want to go ahead and substitute that value in for our variable. So what I'm going to do is substitute that in and solve. So I'm going to end up with 3 times -6y plus 8 equal to 8y plus 11. So if we look at that, we can go ahead and just solve by distributing. What we want to do next, I'm going to go ahead and add 18y to both sides and subtract 11 at the same time. Gets rid of my y's, so I end up with 13 equal to 26y. We divide both sides by 26, and we end up with y equals to 1/2. So we're dealing with some fractions here. Totally fine. We can work with that. So once we get our y, we're going to substitute it back in. I kind of want to use this y and substitute it back into my manipulated bottom equation only because we have the x by itself. So I'm going to go ahead and take that 1/2 and substitute it into my y. So we're going to have x equals to -6 times 1/2 plus 8. So we know that we have to make this a fraction, so -6/1, which when we go ahead and multiply that, we're going to get -6 divided by 2 plus 8. We know that this is going to be a -3 plus 8, and so x is going to be equal to 5. But again, we're not done yet because we have to have an ordered pair. Our ordered pair, remember, is xy, so we have 5, 1/2. So now we're done. Okay, let's move on to the next example, example 2. And now on example 2, if we notice, this looks kind of nice because it's already set up for us in semi-standard form. So when we look at this, all I'm going to do is manipulate my bottom equation by multiplying all terms by -1. So I'm going to keep my top equation, -3x plus y equals to 2. When I multiply this, I'll get a positive 3x minus y equals to a -1. So we should have seen something kind of interesting at the very beginning. If we haven't, hopefully we're seeing something interesting now. And if we still don't, that's okay. So I'm going to go ahead and just add like I've been doing with my elimination. -3x plus 3x, well, that's gone. It's 0. And y minus y, well, that's gone. It's also 0. So on my left side, I'm just ending up with a 0. And then we have 2 minus 1, which is going to be 1. So when we look at this, we notice that we have 0 equal to -1. First of all, we know that that's not true. 0 is never equal to -1. But what does this mean? Well, it means that there's going to be no solution. But hopefully, way back at the beginning, we saw something that was interesting. Both of these are -3x's. Why is that so important? Well, when I go ahead and convert both of these to slope-intercept form, by getting my y by itself, I'll end up with y equals 3x plus 2 for the top, and y equals 3x plus 1 for the bottom. So why is this kind of important? Well, if we look, we notice that they have the same slope. And what did we say about same slope? That's when we see parallel lines. So going back to what we saw when we were first graphing. Again, earlier we saw in this example, they had the same slope. So when we look, remember, our solutions are going to be where our lines intersect. That's going to intersect at 2, -3. Do our lines ever intersect when they're parallel? No, which is why it's no solution. So we know that when we have a no solution, the lines are going to be parallel. So let's look at our very last example. So same kind of thing. It's already written for us in standard form. It doesn't matter which I manipulate, my x's or my y's, because I have a positive and a negative in each. So I'm going to go ahead and just try and get rid of my x's. To do that, I need to multiply everything by 4. So I'm going to end up with 8x plus 12y equals to 24. And since nothing happened over here, I have negative 8x minus 12y equal to negative 24. Hopefully at this point we kind of see something interesting happening. If we don't, let's go ahead and just solve by adding. So negative 8x minus 8x, that's gone at 0. And 12y minus 12y, that's gone at 0. And 24 minus 24 is also 0. So what do we know at this point? Well, I actually have a 0 equal to a 0. So this is true. So what does it mean when our left side equals our right side? That's right. Infinite solutions, all real numbers that are, whatever we want to say. But what does that look like? Graphically speaking. Lucky for us, we already saw this. Back on number 4, what we notice is we had the same y-intercepts. We made the same line. So what does this mean for our equation? That means that we're going to have lines that are coinciding, one right on top of the other. And so whenever we have infinite solutions or all real numbers as our solutions, we know that no matter what point we pick on that line, it's going to make both of these true all the time. So these are going to be coinciding lines. Coinciding. Tough to spell that. I don't even know if it's spelled right, but we got it there. Okay, so that's going to mean one right on top of the other.